Good afternoon. My name is Anna Tiberian. I'm the Vice President and Chief Operating Officer for Beam Engineering for Advanced Measurements Company in Orlando, Florida, and I'll be presenting our development of laser periscope detection system for NAVAIR SBIR Phase 2 program. Beam Engineering for Advanced Measurements Company, or Beam Company, was founded in 1996 by world-renowned scientists in the area of liquid crystals, optics, and displays, Dr. Boris Aldovich and Dr. Nelson Tiberian. It has two facilities in Orlando, Florida, 15,000 square foot laser and optics facilities, and 2,000 square feet chemical synthesis facilities. The company is the pioneer and leader in the area of planar or flat four-generation optics. It has a vertically integrated structure where the development starts at the level of converting raw materials to functional materials in our modern chemical synthesis facilities. Those functional materials are true enablers for fabrication of flat, thin film, near weightless optics and devices that we build with the help of such optics. And those are thin and fast switchable electro-optical components. The applications are multiple. Just to name a few, we have systems that we are developing for defense, for beam directors, for controlling high energy laser beams, for laser protection glasses, for lightweight telescopes, for small payloads, for UAVs, various non-mechanical beam steering devices, and line-of-sight steering devices for surveillance and targeting systems, LiDARs, and laser-assisted active gated systems. Our technology was widely used for ophthalmics. We have developed with our commercial partners adaptive switchable lenses, contact lenses, variable transmission lenses, complex transition and aberration corrected lenses. Our flat optics allows us to have fundamentally different approach to all electronic LiDARs for auto navigation of cars, robots, and drones. Our flat non-mechanical beam steering devices and steering of line of sight of LiDAR allows us to build systems that are more reliable, less likely to break. Augmented reality has been expanding their use of our flat switchable lenses that allow the focus adaptation and creation of various depth perception that is necessary for augmenting the reality with artificial reality. In that area, we have been developing multiple variants of this technology, including transparent and flexible displays. Beam technology is also widely used for space exploration applications. In particular, our devices for non-mechanical transceiver pointing are used for LiDAR for lunar landing by NASA, solar sails and controls, coronagraphs, and ultralight telescopes. Another important application of our technology is optical communications, where our non-mechanical beam steering devices with flat switchable prisms or flat light mechanical devices with our flat prisms allow communication either between satellites, deep space optical communication, ground to space or space to ground for high precision, lightweight systems that allow accurately point free space laser communication devices. The Navy challenge addressed in this program is to meet the following operational need. Detection of periscope masts and proper discrimination of false alarms must be done rapidly before the mast is lowered. Our system is to be fast, with low size, weight, and power consumption. The solution will not depend on optically augmented returns from the periscope optics, and therefore it would not be subject to well-known countermeasures based on spectrally selective filtering or on polarization filtering with the threat periscope. Nor is our approach susceptible to failures due to the periscope detection system being outside the field of view of the periscope, in which case optically augmented signal will be simply not available. The whole concept is based on replacing slow and heavy gimbals with lightweight and fast ALISSA system. On this slide, you see the concept of the operation, which we'll describe in the next slide. Operational concept is based on the following sequence of events. First, there will be handoff from large area search system. Our approach leverages existing deployed Navy airborne and/or shipborne radar systems that are capable of detecting threat periscopes. Then the uncertainty area will be searched with airborne laser imaging system for submarine acquisition that we're developing. In short, it's called ALISSA. ALISSA will provide an independent and unambiguous identification capability. It will also provide an autonomous search capability independent of radar assets. The following step will be image processing of high-resolution laser-illuminated gated images acquired by our SWIR gated camera and automatic target recognition of periscope-like objects, which will be then followed with handoff to the operator. On the right-hand side, you see graphic depiction of the search pattern. In this picture, you see the laser beam illuminating the surface of the water and searching within the uncertainty area handed off by the radar system. At longer ranges, the electronic beam shaper will create a small footprint of the laser on the surface of the water, which would be very much dependent on the range from the aircraft to the surface of the water. The beam from the laser illuminator, as well as the line of sight of the active gated imaging system, will be scanned synchronously to cover the entire uncertainty range in azimuth, and then continue the raster scan with the steps in elevation. And the closer the beam will be approaching the aircraft, the larger will be the footprint of the laser beam on the water. The beam shape and beam profile will be switched electronically by the system that will be developed by beam company. And as we said, the automatic target recognition will be detecting periscope-like objects and handing off to the operator. In order to solve the operational concept, we propose to design and fabricate a field testbed variant of the prototype system for long-range detection of submarine periscopes from high and low altitude aircraft, employing a gated shortwave infrared imager with non-mechanically steered illuminator beam and imager field of view, which we call Airborne Laser Imaging System for Submarine Acquisition, or ALISSA. BEAM is currently developing an electronically scanned periscope detection system utilizing novel breakthroughs in laser systems. in particular shortwave infrared laser range-gated imagers with high resolution, 2 variants of optical path switching to enable detection of periscopes at long range for steering the laser beams and field of views of the imagers, and those include both completely mechanical all-electronic devices as well as light mechanical or quasi-mechanical alternative to counter-rotating Risley prisms, in which we utilize flat alternative to Risley wedges. Those devices provide the opportunities for completely balanced, very fast scanning of the laser beams and the line of sight of the optical imager. Another technology that we are utilizing for achieving the system operation is all electronic beam profile switching to enable laser illumination fluence adjustment with the range. That eliminates the need for large telescopes and for moving mechanisms, moving one lens in a telescope relative to another, thereby reducing significantly the size and weight of the system, in addition to making the beam shaping component completely misalignment insensitive. And of course, discrimination scopes from clutter objects based on high-resolution imaging of periscopes and clutter, and image processing, all that achieved without the use of conventional optical gimbals. The plan for developed system or the packaged variant of them to be considered for employment on platforms such as MH60R or P8A without significant modifications. Here you see the current status of non-mechanical beam deflector breadboard demonstration. We are continuing the construction and characterization of main subsystems that we're developing under this program. On the photograph, you can see SWIR laser rangefinder and imager test bed. The vertical box on the right is the laser illuminator and range receiver apertures, 2-inch apertures. The box in the middle is the 4-inch clear aperture telescope in front of our laser illuminated SWIR range-gated imaging system. The other imaging devices are thermal and visible devices for pointing the test bed at the target at long ranges during the day and night. We are continuing the construction and characterization of prototype non-mechanical beam deflector system that will steer the illuminator beam over the required range of angles on millisecond timescales. In addition to all electronic non-mechanical device, we have fabricated and are finishing construction and soon to start testing of quasi-mechanical or light mechanical alternative to counter-rotating Risley prism scanner, in which we will be scanning our flat cycloidal diffractive wave plate gratings. We also continue construction and characterization of a prototype non-mechanical field of view steerer, which is in this case is large device with 4-inch clear aperture. It will switch the gated imager field of view over the required range of angles in millisecond timescales, and it will be synchronized with the beam deflector in front of the laser illuminator. We are continuing the fabrication and characterization of prototype illumination beam forming system for creating adjustable laser beam fluence as a function of range. We continue development of image processing system with enhanced target identification capabilities. And we are integrating prototype beam deflector, field of view steering, and beam shaping systems with the laser illuminator. We have conducted some preliminary testing in the initial variants of the device and continuing further development.